Hello, Pre-Calc Honors students. Mrs. Myers here. We are continuing our work in section 3 of chapter 7, and we are going to now do a topic called partial fraction decomposition, which I believe you had a little bit of exposure to back in Algebra 2 last year. We're going to actually be doing 2 days of this. So this is day 1 of it today, slightly easier problems today. And then we're going to have day 2 of it Tuesday of next week. Okay, those will be slightly harder problems. So here's an example of a partial fraction decomposition problem. And I'll explain to you what that's all about in case you don't remember it from last year, or in case I'm mistaken and you didn't get a chance to do it last year. Okay, so here's a problem, okay? It's x plus 7 over x squared minus x minus 6. Now, the whole idea of doing partial fraction decomposition is you're trying to tell me what are the fractions that you would add or subtract from each other in order to get this as your answer. Okay, so you're working backwards, essentially. This is the answer to a sum or a difference problem of rational expressions, and you're trying to tell me what those rational expressions are, okay? So the first thing that you need to do is have that denominator fully factored, okay? That is always the first step in partial fraction decomposition, okay? So this is very, very easy factoring. This is just x minus 3 and x plus 2. Now, there's going to be a couple different things that are going on with these problems within day 1 and day 2, and that is, what kind of factors do you have, okay? How many times is each factor being represented in the denominator, and is the degree of the numerator greater than or equal to the degree of the denominator. So today we're going to be doing problems in which the degree of the numerator is less than the degree of the denominator. Okay, so that's going to be important that you take a look at that. And also we are going to only be doing what we call linear factors. Okay, so the type of factor that this is a linear factor because it's degree 1. The type of factor that this is also degree 1. Okay, so this is like the easiest of all problems. It'll just get more challenging from here, okay? So I've got each of these linear factors being represented just one time, okay? So there's no repetition of factors going on here. So this answer must have been a fraction with a denominator of x minus 3 being added with a fraction that had a denominator of x plus 2, right? Those are the two fractions that had to be joined together, added together, that would give you this as the answer, right? Because if you get the common denominator between these two fractions, okay, this would be that common denominator. That's the idea, right? This is the LCD, okay? What were the two fractions that you would add together for which this is the LCD? Now, as long as your factor's just a linear factor, like I said, this is linear factor, degree 1 factor, then your numerator is just going to be some constant, okay? So that's going to be a, we're going to call that some constant a, and this is going to be just a constant numerator again, because it's a linear factor, so we just call that b. It's got to be called something different than this, okay? So the next step is you're going to get the common denominator to go completely across this now fractional equation, okay? So this numerator of x plus 7 over, and keep this denominator factored, x minus 3x plus 2, right? That's going to equal what if I change this to the denominator of x minus 3x plus 2 over, and then again change this to the denominator of x minus 3x plus 2. Okay, so now if I want to go from a denominator of x minus 3 to a denominator of x minus 3 times x plus 2, then what I would have to do is multiply both numerator and denominator here by x plus 2, which means this numerator is now going to become a times the quantity of x plus 2. And again, over here, if I've got a denominator of x plus 2, but this is what I want to get to a denominator of, I have to multiply by x minus 3 over x minus 3, so this numerator would become b times x minus 3, okay? So now I'm going to look at this fractional equation. You see I've got that common denominator going all the way across, right? So if I was to multiply through by that common denominator, I would get it to cancel completely out, and I'd be left with just the numerator right here, right? I'd be left with an equation that would be just those numerators. So x plus 7 would equal a times x plus 2 plus b times the quantity of x minus 3, right? Now, what I'm going to do here is I'm going to clear the parentheses. And I got ax plus 2a, and I've got bx minus 3b. All right, so I've got myself an equation to solve, but it's got two different variables in it. So what do I need to do now is I need to take this one singular equation with two different variables into it, and I got to break it up into a 2x2 system. Okay, I got to have two different equations with those two different variables. So I'm going to rearrange the right-hand side here because I've really got like terms. I've got two terms that have the x variable in it, and I've got two terms that don't. So I'm going to rearrange this into ax plus bx. Okay, and I'm going to rearrange this into 2a minus 3b. Now, these two terms that each have the x in common, I'm going to factor that x out, and it's going to be a plus b. And now there's not really in common there, okay, but I'm just going to put that in parentheses anyway, so that you can now see I've got like terms on each side of the equation, okay? So I've got an x on each side of the equation, a term that has x, and I've got terms that don't have x, right? So in order to break this up into a 2x2 system, I'm going to say, well, if this is 1x over here, and this is x times the quantity of a plus b over here, well, then this a plus b has to equal 1. And then if I've got this constant over here that says 2a minus 3b, and I've got this constant over here that's 7, well, then that 2a minus 3b, that's got to equal 7. And now I've got my 2x2 system to solve, okay? So just as you've done before, I'm going to multiply the first equation through, let's say, by -2, because that will give me, oops, okay, that'll give me the ability to join these two equations together through addition and have those a's cancel right out, okay? So if I multiply through by the -2 there, and I add those two together and the a's drop out, and I've got myself -5b equals +5, divide by that -5, and b is equal to -1. Now I got to go back and I got to substitute and get the a value. So if a plus b has to equal 1, and now I know that my b has to equal -1, then I have my a that has to equal 2. And now I can say that this fraction x plus 6 over x plus 7, sorry, over x squared minus x minus 6, which is really x minus 3 times x plus 2, okay, had to have come from, so my value is 2, put it back in, had to have come from 2 over x minus 3, okay, being added with -1 over x plus 2. All right, and granted, of course, I can write this as -1 over x plus 2 instead, okay? So this is the partial fraction decomposition. If I was to get a common denominator between these two fractions, okay, and then add those two fractions together, this would be my answer, okay? So that's the idea. So let's try one more. All right, let's go with 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x. Okay, so let's do the partial fraction decomposition for that problem. So that is the answer to the addition and subtraction of two fractions, or maybe even more than two fractions, okay? So the first thing I want to do is I want to completely factor this denominator, and I can see that they all have an x there, right? So the fact that they all have an x, I'm going to do GCF factoring first, okay? And then this is actually a factorable trinomial, and it factors into two identical binomials, which actually means I'm going to write it like this. Right? X times x plus 1 quantity squared. So the thing is, what this has to partially fraction decomposition into is three fractions. Okay, you might think it's only two because I've got this factor here that's an x, so that's one denominator, and I've got this factor here of x plus 1, so that's another denominator. But the thing is, I've actually got a factor of x plus 1 quantity squared as well. Actually, what you're probably thinking is just this. It's just the x and then the x plus 1 quantity squared. But the thing is, this is what's called a repeated factor, okay? You've got x plus 1 occurring twice, but you could have had a third fraction in there that would have a denominator of just x plus 1 being added to these two fractions right here that had denominators of x and x plus 1 quantity squared, and that still would make this be the LCD, okay? So you got to account for every time, every power that this could have been repeated up till. So that if this was x plus 1 quantity cubed, okay, then you would have to have x plus 1 quantity squared as a denominator, and then just plain old x plus 1 as a denominator as well, because you would still have this as the LCD of all of them. Now, it might turn out that you don't have this as an answer. You might get this numerator value to be a 0, but you might not. So you got to account for the possibility of it though, okay? Now, these are all just linear factors, Okay, this is plain old x, this is plain old x plus 1. These are just powers of 1 on the x, so these are just linear factors. So these are all just constants as numerators, just a, b, c, and I'm going to go from there, okay? So I now have 5x squared plus 20x plus 6 over x cubed plus 2x squared. Oops, I want to write that in factored form. Sorry about the delay here. So I want to write this as x and then x plus 1 quantity squared. All right, so anyways, I'm going to come over here and I'm going to write each of these fractions as x plus 1 quantity squared. And then I'm going to adjust the numerators as needed. Okay, so for this first fraction right here, okay, I only had a denominator of x, but I want to get to this denominator. So that means the numerator is going to be multiplied by x plus 1 quantity squared. Okay, now over here, I have a denominator of x plus 1 quantity squared, but I want to get it to be x times x plus 1 quantity squared. So that numerator of b is going to be multiplied by the x. And lastly here, I've got my x plus 1 denominator, but I want it to become x times x plus 1. So that numerator of c has to be multiplied by the x, and it has to be multiplied by another x plus 1 quantity to get from x plus 1 to x plus 1 quantity squared, okay? So now that I've got that common denominator all the way across, okay, I can basically say that all these numerators would give me an equation. So I've got 5x squared plus 20x plus 6 equaling a times x plus 1 quantity squared plus b times x plus c times x plus x plus 1. All right, and I'm just going to now clear all those parentheses and see what it gives me. Okay, so this is going to be x squared plus 2x plus 1, right? And I'm going to distribute the a into. So this is ax squared plus 2ax plus a. And I've got my bx. And then here, this is going to be cx squared plus cx. All right, so I've got 3 different variables to solve for, right? A, b, and c. So I've actually got to write a 3x3 system here. Now, how I'm going to do that is I'm going to rearrange and look to see what like terms I have on each side of the equation. Okay, so I'm going to group together, I'm going to rearrange the right side, I'm going to group together the x squared terms, ax squared and cx squared are going to go together. Then I'm going to group together all the plain old x terms, so 2ax and bx and cx are going to be grouped together. And then I've got just that one lonely constant right here of just the a. So these have an x squared in common, so that's a plus c. All these have an x in common, so I'm left with 2a plus b plus c. Okay, and when I look at what that is set equal to on the other side of the equation here, I've got an x term, an x squared term, an x term, and a constant. So I've got my 5, which has to equal a plus c, right? So this is what x squared is being multiplied by over here, and this is what x squared is being multiplied by over here, so those have to be the same. Then I've got this 20 that has to equal the 2a plus b plus c, right? And then I've got the constants, so that means 6 has to equal a. So this is actually a super easy 3x3 system because I've already got one of the answers right here. And I can just substitute that into the first equation and say 5 has to equal 6 plus c. So now I know c has to equal -1. And then finally I can get b by just plugging them in here. So I've got 20 equals 2 times my a value plus my b value plus my c value. So 20 equals 12 plus b plus -1. So 20 equals 11 plus b, so b would have to equal 9. And then I just write my equation. I write my partial fraction decomposition, I should say. So I've got 5x squared plus 20x plus 6 over, the x cubed plus 2x squared plus x, which factored into x times x plus 1 quantity squared. So it must have been, here's my a value of 6. Okay, it must have been 6 over x. Okay, b value is 9, so it must have been plus 9 over x plus 1 quantity squared. And then it must have been minus, the other c is -1, minus 1 over x plus 1, okay? So if I actually took the time to get the common denominator for all 3 of these fractions, adjust the numerators as needed, then put them all together, that would be the answer, okay? And it really wouldn't matter what order you write all those in, okay? So that would be your answer. All right, so that is day 1 of this with 2 problems that were, a little on the easier side, not easy, but easier than the ones that we're going to go through for day 2. All right, so hope you understood this, and hope you do okay with the problems that follow, and I hope everyone is doing well. Until the next time, bye.